Hi, I'm Pranav. I'm an EC student at TIT Thapar, and I'll be presenting the Capstone project for group number 10. So let's meet the team.
Hello everyone, I am Amaani Chaudhary. My roll number is 1021860001.
Hello everyone, my name is Lakshya Garg and my roll number is 102056006.
Hello everyone, I am Sahil. My roll number is 1021860005.
I am Vedika Sharma and my roll number is 102006193.
So here is our Capstone project. Our project is titled as FPGA based laser jamming system. Before we begin, I'd like to thank Dr. Anil Singh and Dr. Manu Bansal for their extensive support throughout our project. So let's begin. Before we begin, I'd like to explain the theory behind our project. Consider the figure shown before you. Here we have an airborne plane targeting a ground station. The dotted line represents a transmitted laser and a solid line represents the reflected laser beam. Any missile that's been launched towards the target will use this reflected laser beam to guide itself towards the target. In order to jam the laser, a different laser beam will be emitted towards the plane, which will be higher in SNR ratio, which is signal to noise ratio, and will have a lot more power than the reflected beam. This will divert the missile away from the target and hence jam the missile. Currently, a whole assembly is required to jam a single missile. Using our capstone, we intend to jam up to 4 lasers concurrently. Another factor is the delay. Our capstone drastically reduces the delay in jamming a laser frequency, which is very important in these crucial times. So let's see how the internals of the project work. So here is our proposed approach. Before you is a top level design of our project. Let's see how the system works. We are implementing our project on a basis 3 FPGA board. We have found that the FPGA board is a flexible tool that can help us jam our frequencies. So our FPGA board is divided into two modules. The first module is the test module, which consists of a signal emulator and a signal receiver. A signal emulator will be used for simulation purposes only, wherein it will be required to generate random frequencies that we can test upon our current design. Approaching to the main design, we have the concurrent laser missile jamming system. This consists of multiple modules, the first one being a processing unit, the second one being a conversion module, and the third one is a display module. The processing unit consists of the major processing which takes place inside the FPGA board. The conversion module merely converts the values into displayable characters, and the display module shows the output on an LCD display. Going into our processing unit, a lower level design, we have a phase lock loop which is used to increase the frequency of our basis 3 FPGA board. Currently, it can be only operated at 100 megahertz, but using our phase lock loop, we can increase the frequency up to 400 megahertz. We have a pulse detector module that can detect the frequency of our incoming laser beams. We've also used an input data buffer that can minimize the time which is required between jamming consecutive laser beams. This also helps in reducing the number of times the memory is accessed, because each time memory is accessed, it increases the delay in jamming the system. Moving on, we have our frequency calculator. This particular module uses a basic formula that counts the number of oscillations from 1 to 0 under 1 second. This will calculate the frequency of the input laser beam. It is surrounded by a clock generator which has an input of 100 megahertz that the basis 3 produces. This 100 megahertz acts as the reference frequency on which our phase lock loop operates on. Lastly, we have a pulse generator which uses these clocks and input variables and produces a pulse width modulated wave that has the same frequency as the input signal but has a higher power and a higher signal to noise ratio. This effectively jams. All the previously shown modules were coded in Verilog and were simulated using Xilinx Vivado tool. Before you are the results of our project. Firstly, we have the results of our frequency detection module. The input supplied to the clock was 100 megahertz, and the input in our frequency was a 50 megahertz frequency detection. As you can see, our frequency highlighted here shows a 50 megahertz output, which shows that we have successfully detected the incoming frequency. Further are the results of 20 megahertz frequency detection, 70 megahertz frequency detection, and also 400 megahertz frequency detection. Another window here shows our outputs that will be transmitted towards our laser beam. These are pulse width modulated outputs which have the same frequency as the incoming laser beams but a very high duty cycle as compared to those inputs. These have a lot more power than the input beams, which can use to jam the missile. So let's see how the working prototype works. So here we have our prototype. Here you can see we have 4 airborne fighter jets representing planes, and underneath those planes we have attached 4 laser emitters. And these laser emitters are targeting one singular ground target. We have represented that using this black box, and surrounded by these black boxes are our laser receivers placed on the north, south, west and east ends of the box. Here we have our LCD display that can emit our final outputs of the frequencies that are emitted by those laser emitters. Now, if you look underneath the base layer, we have our circuitry which we have managed to hide well. Our circuitry involves a basis 3 FPGA board, our phase lock loop, and some other aspects including breadboards, wires, and also an Arduino circuit. So here you can see the outputs containing frequencies of all the received inputs of lasers. Here we have missile 1 showing as 50,000 hertz, missile 4 100,000 hertz, and so on. So this can demonstrate the working of all our input laser missiles. And for our outputs, we have managed to connect those outputs to the output pins of the basis 3 FPGA board, and they can be relayed to an external laser emitter that can be placed on a far location which is very far from our desired target, and thus it can jam any missile that's coming towards it. Thank you.